In this video we're going to investigate the relationship between force and acceleration. For a constant mass, the relationship between force and acceleration is this. Force is mass multiplied by acceleration. It's important to note that this is the resultant force and the resultant acceleration. And with thanks to Dr. John Nunn of the National Physical Laboratory, he's given me permission to use this simulation to gather results so that we can investigate this equation. Now in this simulation what we've got is two light gates, one on the left, one on the right. These light gates turn a timer on for the duration that the light beam is cut. In other words, when the light cannot be detected at the timer is running. And that's also true on timer 2. But there's another timer that detects the time between this light gate on the left being broken and the light gate on the right being broken. Now this car is connected with a thread through some pulleys to some weights that are suspended at the end. Right now there are 5 newtons suspended from this string, but I can increase that to 10 newtons. 10 newtons being the weight of approximately 1 kilogram, or 10 of those laboratory 100 gram slotted masses that you can get. Now you'll notice that when I increase the number of masses suspended on this string, the number of masses on this car on the left reduces and vice versa. And that's because the force, the weight of these masses that are suspended over the edge, that force is going to accelerate not only the car, which is connected with this thread, but also those weights that are suspended over the edge themselves. And so because we want to investigate what happens when we have a constant mass, when m is constant, we need to make sure that the mass being accelerated never changes. So let's start with the highest force, because that way we can see things moving most quickly. Let's start with 10 newtons. When I release this, we'll see the 10 newtons accelerates this car, and this car moves from one light gate to the next. You can see as it passed through the first light gate, the timer of the first light gate was running, and the same for the second light gate. We also have the time between the 2 light gates given here. Let's take that data down in a table. Now we can write down our force of 10 newtons easily enough, but what was the acceleration? Well, we'll have to calculate that. The definition of acceleration is the rate of change of velocity. So that's the final velocity minus the initial velocity, all divided by the time between those 2 velocity measurements. The initial velocity at timer 1 is the distance that the car has travelled, or should I say the car's displacement, because we are talking about velocity, divided by how long it took to pass through that light gate. The displacement, as you can see from the ruler at the beginning, was 10 centimetres, because the car itself was 10 centimetres long, and the time it took was 0.49 seconds. Now GCSE students at this stage may find it easier to convert centimetres into metres, so 0.10 metres divided by 0.49 seconds. That gives us an initial velocity of 0.204 metres per second. 0.204 metres per second. Now the final velocity over here can be found using the same method. It's the same 10 centimetres distance because the car is the same width, but the time is now much less, 0.15 seconds. Again, GCSE students often find it easier to convert at this stage into metres, and our time is 0.15 seconds, and that gives us a final velocity equal to 0.667. 0.667 meters per second. And what you'll notice is I've given my velocities to one extra significant figure than the precision of the numbers I used in my calculation, and that's because these are intermediate calculations. That means that these calculations are not the final result, so I keep an extra significant figure so that if there are any slight differences caused by rounding, it's not going to affect my final result. The time in between these 2 measurements of velocity, t, is what's shown on timer 3. So that is 2.27 seconds. And we can plug all those numbers into our acceleration equation here. So 0.667 minus 0.204 0.204, all divided by our time of 2.27 seconds, which gives us 0.204 meters per second squared, 0.204 meters per square second. And that's our acceleration when we had 10 newtons of force. So we can now put that on our table, just like this. Now we have to do the experiment again with a different force. Let's reset this, and this time let's go down to 8 newtons. And what we'll do is we'll reduce by 2 newtons each time. So here are our data, here are the times, and when we do the same method we did last time, we get an acceleration of 0.161 meters per square second. That's for 8 newtons. Now let's look at 6 newtons. One thing that's important to note is that we're going to use the maximum possible range of weights suspended over the edge. That gives us the maximum possible range of accelerations, maximum possible range of forces, which should make our final result as accurate as it can be. You'll notice that I'm going up in stages of 2 newtons. I could have gone up in stages of 1 newtons. So here are the results for my 6 newtons, I believe it was. And so let's write these in here. 0.117 meters per square second. And we'll carry on. We'll look at 4 newtons, 2 newtons, and we'll also look at 1 newton at the end as well. Now that will give us, I think, 6 results. Really, we should need 7 results, but I don't think it really matters for this particular experiment. We're going to get a pretty nice straight line as it is. Now there is an effect that happens that I haven't really shown very well in this simulation, which is the effect of friction. Because remember, we are looking at the resultant force acting on this car, but the car experiences friction as it is moving along this path. Not only that, there is static friction, which has to be initially overcome for the car to start to roll. If you consider, for example, my board here, if I place my phone on it and I tilt it, the phone doesn't start to slip, despite the fact that there is a component of the gravitational force acting down this slope. There's also a component of static friction acting up this slope, and that can take a maximum value. You'll notice that still the component of static friction up the slope must be equal to the component of the weight down the slope, because it isn't accelerating down the slope yet. But if I continue to tilt this, eventually it suddenly slips. Now I've chosen a surface here with quite a lot of friction, so that I get quite a steep angle before that weight component down the slope is equal to the static friction up the slope. With your car, it's got wheels, so it's got much less friction. And so because of that, you'll need far less of an angle to compensate for that friction. We call it friction compensation. And the way it works is you place your car on the ramp with no other forces acting on it, and you tilt the ramp until just before the car starts to roll. If the car starts to roll, you've tipped it too far. You go back a little bit more, and that way the car, any static friction acting on that car has been compensated by that component of weight acting down the slope. So static friction aside, let's carry on taking our measurements. This is an acceleration of 0.0806. Now I'm going to give this to 3 significant figures, which means that I'm not being consistent with my decimal places. And I've chosen to do that because I used numbers in my calculation that were 2 significant figures, and so I've kept an extra significant figure in my calculation. Doing so, as I've changed my order of magnitude here, means that I've had to add an extra decimal place on. It's okay to do that because column A here, the acceleration, is calculated, not directly measured. Now, if you've ever done this experiment in a lab, this is 2 newtons acting on this car. You'll know that it seems to accelerate far quicker than this looks like it's going. When we calculate the mass of this car, I think we'll see why that is. So let's do the calculation while the car is running. 0.1 meters is the distance at time of 1 divided by 1.11 seconds. That tells me the initial speed. and I need to subtract that from the final speed, which is 0.1 divided by 0.34, and that gives me 0.2040 blah blah blah, and then I divide that by the time between the two light gates, and that gives me my acceleration, which I can add to this table here. And now let's get our last result. So we have the maximum range of measurements. Let's load this up, reset, put 1 Newton on it, release. This might take a while. As you can see, it's barely accelerating. It's just reached the first light gate, 10 centimeters of distance through the light gate. Took a whopping 1.56 seconds. So let's do the calculation. Initial speed is 0.1 divided by 1.56, which is 0.0641 meters per second. Just arriving at the second light gate there. And so that's 0.1 meters divided by 0.48. That gives us 0.208 meters per second. Take the difference, which is 0.1442 meters per second, and divide that by the time between those two measurements, 7.16, which gives me my acceleration. Okay, so I have 6 measurements. Really I should have 7, but I've got the full range and there's a sensible interval between each, so that's fine. Now, what would I plot on my graph to confirm that this equation works? In this equation, we kept mass constant. So I'm going to use my highlighter pen and colour that blue. And what I varied was the force. So that's a variable, which I'll colour yellow over here. And the acceleration changed as a result, and I measured that. So I'm going to colour that in yellow as well. Our independent variable in this picture was our force. Our dependent variable was our acceleration. And that made mass the control variable. I could have changed the mass, I could have just put more mass on the car, but I chose not to. I chose to keep that the same. Now, our favourite equation, a physicist's favourite equation, is y equals mx plus c. That's the equation for a straight line. And the form of that equation is a variable, here in yellow, is equal to a constant times by a variable and then added to a constant. Now that constant can take any value. It could even take the value 0. And if c equals 0, I hope you can see that the equation y equals mx is in the form variable equals constant times variable, which is the same form as the equation f equals ma. So if I were to plot on the y-axis the force, and I were to plot on the x-axis the acceleration, the gradient would be the mass. Conveniently, m is for the gradient and m is for the mass. Funny how that turned out. So what we're going to plot is a graph with force on the y-axis. We're going to do this even though force was an independent variable, and therefore you may believe that the force should be plotted on the x-axis, because by doing so we should get a nice straight line. Now, in an ideal world, the y-intercept would be 0, but it might not be. It might be some unknown amount of force that gives rise to 0 acceleration, whatever that may be. But then we've also got our gradient here, and our gradient will equal the mass. Incidentally, we could actually work out exactly what this additional bit of force represents in terms of physics, because we didn't do any sort of friction compensation. And so if there's always the same amount of force we have to overcome just to get any sort of acceleration, then that would show us with an intercept on the y-axis, a systematic error, we call it, a systematic error of the static friction. If you think about it in terms of the physics, if I'm applying a force, whatever that y-intercept is, but getting no acceleration, that means that the resultant force at this point must be 0. I'll just change the colour of pen so I can say what I'm talking about. At this point where the force on the y-axis is not 0, the resultant force must be 0 because the acceleration is 0. So this additional bit of force must be the force that is exactly equal to the static friction force. So I've just gone ahead and copied those data into my spreadsheet, and now I'm going to plot on the y-axis the force. Unfortunately, because I want to plot force on the y-axis, I actually have to swap these columns around a little bit. Sure, because in Microsoft Excel, the column to the left is always assumed to be the x-axis, and the column on the right is always assumed to be the y-axis. And that's correct. You should always make sure that your independent variable is in the column to the left, and usually, you would plot your independent variable on the x-axis. But in this case, we're doing it the other way around, so when I plot this, I've had to switch this around. In Excel, it's straightforward. You select your cells, and then you select, hopefully you can see this if I move this around a tiny bit. You select Insert, and then you can select your scatter. Even though we want a line, we're not going to choose line because that assumes it's a categoric variable on the x-axis. I'm going to delete the title because I'm not interested in the title. And there we can see that we've got our force on the y-axis. Now at this stage I could go through the palaver of labeling my axes and making it look pretty, but I'm just using this as a tool to get some data, so I'm not so worried about that. If I select the data points, right click and choose Add Trendline, then it gives me a menu on the right hand side that looks a little bit like this, and I'm aware my face is covering it a tiny bit here, but you get the idea. I'm going to choose linear because I want a straight line. That's the default, and I can just choose to display the equation of this straight line on the graph. And there it is. There's the equation of the straight line. If I make the font a little bit larger so we can actually see it, there we have it. And so that equation is in the form y equals mx plus c, where the intercept is given as 0.0552. So that is in newtons the force of static friction. Notice it isn't very much, but it's there. That's the force of friction that's been overcome. The line isn't straight through the origin, although it's jolly close. We also have this value here, which is the gradient. Now, we added a kilogram, or near enough a kilogram, onto our car. If we have a look at the simulation again, we had, when we had all 10 newtons suspended over the edge, no weights in the car. When I had just 1 newton hanging over the edge, the rest of the weights were all over here in the car. So the mass of the car is going to be the mass that we've calculated from, or determined from our graph, minus the mass of the weights that we have suspended over the edge. 10 newtons is the weight of approximately 1 kilogram, so this is approximately 48.236 kilograms worth of car. That is a tremendous mass for that car, and it does explain why it accelerated so little as it experienced that force pulling it along that ramp. So that is how you can determine the mass of the car using this equation. And it also confirms this equation was correct. F does equal ma for a constant mass because we had a straight line. But what if I wanted to do an investigation where I didn't keep the mass the same? Instead, I changed the mass but kept the force I was accelerating the car with the same. Well, in that case, what we'll do is we'll make sure we have the same amount of mass suspended over the edge of the bench, so we have the same force acting on this car, and we will simply increase the amount of mass on this car bit by bit and measure its acceleration and see the relationship between mass and acceleration that way. Now, in that case, our equation F equals ma, which we hope is the same, we have to look at it differently because now we're keeping the force the same. We're not changing the amount of weight hanging over the edge of the bench. That's a constant. And if that's the case, then our variables are the mass of the car, because we're increasing it or decreasing it, and the car's acceleration. Now, we do exactly the same experiment in terms of measuring acceleration as you've just seen. But in order to analyse the results, what do we plot? Well, we need to get this equation in the form y equals mx plus c. So in that form, The variables are y and x, and the constants are m and c. And remember, c can take the value 0. So if we assume c is 0, and if it's not, we'll figure it out why later, then we have to rearrange this equation. We can either say acceleration is equal to force multiplied by 1 over mass, or we can say we can say that mass is equal to force multiplied by 1 over acceleration. In both cases, the force is constant, and in both cases, we're plotting a variable equals a constant times a variable, because if mass is a variable, then 1 divided by mass is a variable. Or if acceleration is a variable, then 1 divided by acceleration is a variable. And so on our graph, it doesn't actually matter which way round we plot it. The gradient will still be the same thing. If we plot acceleration versus 1 over the mass, then we'd expect a line that does this, and the gradient would be the force that was applied to that car. If, however, there is a non-zero origin, so there is some y-intercept, should I say, then we're saying there's some acceleration even though, for a given force, even though we've got an infinite mass, which wouldn't make much sense, I suppose, this way around. If we plotted it the other way around, and put mass versus, let's try it this way around, mass versus 1 over acceleration, then what we're saying, if there's some non-zero intercept, is we are saying that we would get infinite acceleration for a non-zero mass. And I suppose that might be, you might be able to get funny results like that happening if we don't take into account things like the mass of the string, but it's minuscule, absolutely minuscule. So this is the required practical for most exam boards now, investigating how mass, acceleration and force relate to each other, or Newton's second law. Thank you very much.